All right, so we just talked about, or we just wrapped up kind of physical and chemical properties and physical and chemical changes. Now we need to talk about these intensive and extensive properties. An extensive property depends on the quantity of a sample. So good examples are mass, volume, and length. So you're talking about the extent of a substance. Now, an intensive property is independent of the quantity used to define the sample. So density, boiling point, and color. Okay, so the way that I always kind of think about these is, well, first of all, I think of the word extensive and I think extent. So the vastness of something. And so you can have, and you would describe something with a chemical property as well as an extensive physical property. Something can also have an intensive property, something that's intrinsic, something that makes that property unique. And I always think about density as that. Okay, so density, effectively, as an example, will never change whether you have, like, think about the density of water. The density of water is 1.0 grams per milliliter. Okay, so that means if you have 1 milliliter, that 1 milliliter has a mass of 1 gram. So we've got this kind of magical ratio, grams per mil, 1 gram per milliliter. Now, if you've got a 12-ounce glass of water, what's the density of that? Well, it's still, the density is going to be 1 gram per milliliter. Will this have a mass greater than 1 gram? Absolutely, because you have a volume greater than 1 milliliter. Okay, so the density is 1 gram per milliliter. Now, what if you have, let's say, a 44-ounce, one of those mega drinks from Stripes? Well, that water is still going to have a density of 1 gram per milliliter. Each single milliliter will have a mass of 1 gram. So no matter how much of this you have, that is not going to change. Likewise, the boiling point, or melting point for that same matter. If you have an ice cube that's as big as a house, well, that's going to take a lot longer to melt than something that's the size of this little cube here. But nevertheless, that melting point is going to be at 32 degrees Fahrenheit. At 32 degrees, it's going to begin the transition from a solid to a liquid. That boiling point or that melting point doesn't change based on the amount of it. All right, so after that, we can talk about solids, liquids, and gases. So think about a solid as something that's going to pack really well into a specific space. A liquid, and a solid is going to have a very strict, rigid structure, whereas a liquid, well, it's a little bit, think about these as displaying the same number of these green spheres. As a solid, there's a set shape, it's very rigid, they're compact, whereas a liquid, well, do these green spheres, do they fill the same space as this? No. In the liquid, they go all the way to the edges, there and there, whereas in the solid, they don't. They have a defined shape. Okay, compare that to the gas. Well, the gas is going to be, well, filling as much space as it possibly can and as much as it needs to. So that's our difference on the molecular level between solids, liquids, and gases. Okay, solids are going to have a definite volume, a definite shape. Particles are going to vibrate around a fixed position but do not move past one another. The spacing between these particles is very, very small. They're going to be as compact as possible. Okay. Now, a liquid, you've got a defined volume and indefined shape. So they're going to basically move to whatever shape you can, whatever they can adapt to. Particles are going to be moving all over the place, and the spacing between these particles is similar to the solid, very small. Okay. Finally, our gases. They're going to have an indefinite volume, an indefinite shape. Particles are going to move past one another, and the spacing between them is going to be pretty significant. It's pretty large. So they're going to, one thing that we know about gases is they're going to fill the container in which they're found. All right, so the way that I always think about the difference between these is I think about if somebody put like when I was in middle school, people would bring little stink bombs, and they'd like break one off in the bathroom or something, and it would, you know, fill basically the whole school, and we'd have to leave the school because it smelled awful. No hazard, no hazard other than that it smelled awful. But that gas, well, it vaporized and it spread out and it filled the entire shape that it was in. The shape was the building. So it filled that, the volume was indefinite because it would fill the volume of the containing subject, the building. Okay, mass and weight. How to relate these two things to one another. Mass measures how much is in a object. Weight is how strongly gravity pulls on an object. Now, I will confess that I do sometimes slip up and refer to or substitute mass and weight for one another, which is incorrect, but I'll try to keep a lockdown on it. But know this definition. Mass measures how much matter is in an object. Yeah, there we go. Chemists use these two interchangeably because we're stuck on Earth. And, well, I don't know if I'd say stuck. I enjoy it here. It's all right. Energy is the capacity to do work. So energy can also be displayed as heat, chemical energy, nuclear energy, kinetic energy, or sorry, mechanical or kinetic or potential energy, electrical energy, sound, or electromagnetic radiation. We'll cover all of these over the course of the semester, either in Gen Chem 1 or Gen Chem 2. The law of conservation of energy. Energy cannot be created or destroyed, but it can be converted from one form to another. For instance, heat energy can be converted to kinetic energy. You know, heating something up can cause something else to move. All right, well, I hope this is helpful, and we'll continue on in the next video. Thank you very much.